Hello everyone, and welcome to a new instalment of Teach Me in 10, a video series brought to you by LabTube, part of the Technology Networks group, where we ask scientists to talk about a scientific research area or concept in less than 10 minutes. My name's Karen, and I'm a senior science writer for Technology Networks. I'd like to welcome back our guests for this video, Abe Gutierrez and Ed McCurdy from Agilent Technologies, with part 2 of their Teach Me in 10 talks on ICP-MS, this time focusing on Triple Quadrupole ICP-MS.
Thank you, Karen. Welcome to a part 2 of Teach Me in 10 series on ICP-MS. Today with Ed McCurdy, we will be talking about ICP Triple Quad.
On our first video, we discussed the theory of ICP-MS and how it works, and how it can measure almost every element in almost any sample type, including solid, liquids, or gases. If we can measure almost every single building block of matter in just about any matrix, why will we need an ICP-MS triple quad? That's what we're going to be discussing today. First of all, what is a triple quadrupole? According to the International Union of Pure and Applied Chemistry, a triple quadrupole is a tandem mass spectrometer comprising of 2 transmission quadrupole mass spectrometers in series, with a non-selecting RF-only quadrupole or multipole between them acting as a collision cell. LC-MS-MS and GC-MS-MS measure fragments of organic molecules, so you usually use collisional gas. ICP-MS-MS separates elemental ions from spectral interferences, so we often use reaction gas. There are many benefits on using ICP triple quad, but the key feature is that it's a tandem MS, operating in MS-MS mode, which means that you can apply 2 mass filtering steps, one before the cell and one after the cell. When comparing the two, it's always good to know that the triple quadrupole can do everything that a single quadrupole can do, but better, because it's going to have higher sensitivity and lower background. So when using helium mode, they both are going to do a great job. But if you're using reactive gases, not having control of what enters the cell, you have no control what's going to exit the cell. What's going to happen is that you're going to have many different ions coming out of the quadrupole, and now the spectrum is going to be more complex. It's going to be harder to know what's real and what's not. Having the triple quad using MS-MS, now you control what enters the cell. That first mass filtering step is going to kick everything out of the way but the element of interest and the interference. Having that control means that you can predict what comes out of the cell. On a well-designed experiment, only the target ion makes it out of the quadrupole into the detector. So the ICP triple quad gives you more options for controlling and resolving spectral interferences. Controlling and reducing these interferences is crucial for the generation of quality data. Having that additional mass filter before the cell, it means that you're going to be selecting what passes to the cell. So the reaction process in the cell is going to be controlled. On a single quad, not having that additional mass filter, it means that you have no control what enters and reacts in the cell. So you're going to have new product ions being formed. The number of complexity of these product ions is going to be depending on the matrix and the reactive gas that you're going to be using. If you use a gas like ammonia, which is very reactive, this is going to be undergoing subsequential reactions, and you're going to be forming many overlapping cluster ions. As you can see in this table, you have the different cluster ions formed by ammonia and the cluster ion formed by ammonia with titanium, vanadium, and chromium. The squares that you see with the same color are cluster ions of the same mass. In the case of 84, you're going to have a cluster ion of titanium 50, of vanadium 51, and chromium 52 showing up at the same mass. Now, Let's go to Ed McCurdy. He's going to show us some examples of where these capabilities move the game beyond a single quad. Ed, take it away.
Thanks very much for the introduction, Abe. I'd like to focus on three main areas where ICP Triple Quad provides superior performance compared to Single Quadrupole ICP-MS.
The first is where the higher sensitivity and lower backgrounds can give us improved detection limits. The second is where we use reaction chemistry to improve the removal of some spectral interferences. And the third is where we utilize the fact that we have two mass filters, and the double mass selection gives us much better resolution of adjacent mass overlaps. If we look at those three in turn, let's look at lower detection limits first. There are many application areas where higher sensitivity is beneficial for ICP-MS. Maybe the most obvious group is where we're measuring ultra-trace contaminants in high purity materials and reagents, but also applications where we need to measure ultra-low level trace analytes such as geology, nuclear, environmental and food contaminants, and also any application where the amount of material delivered to the ICP-MS is reduced, for example because we've done a chromatographic separation or small crater laser ablation, or where we're measuring single nanoparticles or single cells. Moving on to the control of reaction processes to give us better removal of interferences using reaction mode. The first comment to make is that remember, most spectral interferences in ICP-MS are polyatomic ions, and these are mostly removed very effectively using helium collision mode, as illustrated in the spectra here. But there are some spectral overlaps that are not removed effectively in helium mode, and for these, using a reactive cell gas can be beneficial. The first example is an illustration of the resolution of what we call isobaric overlaps, which is where two elements have an isotope at the same mass. And this example is where we want to measure the minor isotope of lead at mass 204. This is a measurement that is needed in some geochemical applications. We can't measure lead 204 on single quadrupole ICP-MS if there's any mercury present, because mercury also has an isotope at mass 204, which overlaps the lead 204. If we do the analysis using ICP Triple Quad with ammonia cell gas, we can react the mercury with the ammonia cell gas, neutralize the mercury, remove it from the mass spectrum, and therefore measure the lead, including the minor 204 isotope, accurately and free from interference. We can't use that same cell gas approach reliably on single quadrupole ICP-MS because ammonia is so reactive. So if there are any other ions present in the cell, the ammonia will react with them and form product ions that overlap on the masses that we're trying to measure. And also the lead 204 and mercury 204 isotopes are so close in mass that it's impossible to resolve them using high resolution ICP-MS. The next example is the measurement of sulfur. Sulfur 32 doesn't have any direct isobaric overlaps, but in normal single quadrupole ICP-MS, it does suffer from a very intense background signal from the O2 ion. So two oxygen 16s form an ion at mass 32, which overlaps the sulfur. There is one possible approach that we can use to avoid this, which is to use oxygen cell gas. But if we use this method on single quadrupole, we can move the sulfur successfully to its SO product ion. Sulfur 32 plus oxygen 16 gives us a product ion at mass 48, but on single quad that is also overlapped by other elements. So for example, calcium 48, titanium 48, argon, carbon, and so on. So either direct analysis at mass 32 or use of the sulfur oxide product ion at mass 48, neither of those gives us accurate trace analysis of sulfur using single quadrupole ICP-MS. If we do that same oxygen cell gas method for sulfur analysis, but this time using ICP-MS, we're still using the same reaction chemistry process. So we're measuring sulfur after converting it to its sulfur oxide product ion. We're measuring it at mass 48, but by using MS-MS, we can reject all of the other ions that would overlap with the sulfur oxide product ions at mass 48, 49 and 50. By the way, because the reaction process is so well controlled with ICP triple quad, we do get accurate analysis of all of the sulfur isotopes at low level, right down at single ppb level, even though this ethanol solution was not particularly clean. There is a sulfur blank level present. If you have a reagent that is high enough quality, so low enough sulfur contamination in the blank, this method, this sulfur oxide product ion measurement using ICP-MS can get you down to single part per trillion detection limits. So really many orders of magnitude better than what we can achieve on single quadrupole ICP-MS for sulfur. Moving on to the third group of applications where ICP triple quad gives us a benefit, which is the improved resolution of peak tail overlaps. The example I'd like to use to illustrate this is the measurement of trace manganese, which is measured at mass 55, in a 1000 ppm iron solution. Iron that has its major isotope at mass 56, and you can see from this spectrum here in single quad mode that the low mass tail of iron tails across the manganese peak and interferes with the measurement. Now that's despite the fact that the quadrupole we use in ICP-MS is a very efficient, very effective mass filter. It rejects all but 1 out of every 10 million adjacent mass ions. So in this case, the iron is just so intense that it is making a contribution to the adjacent manganese peak. If we utilize ICP triple quad, we have a double mass filter, so Q1 before the cell and Q2 after the cell, and both of those are using or delivering a mass filtering efficiency of rejecting all but 1 of every 10 million adjacent mass ions. So the total contribution of those those 2 mass filtering steps is that even in the presence of a very intense iron peak from 1000 ppm iron, we can completely baseline resolve the trace manganese peak using ICP-MS. So in summary, what is ICP triple quad? It is a tandem mass spectrometry system that operates in MS-MS. It does everything that single quad can do and so much more. And as we've seen, the major contributions are improved detection limits, control of reaction chemistry to resolve some spectral interferences that helium mode can't deal with, and also dramatically improved peak resolution to resolve those adjacent mass overlaps. Thank you very much for your attention.
Thank you both so much for joining us for Teach Me in 10 and for another excellent talk. For anyone who would like to see part 1 and an introduction to ICP-MS, you can find the link in the video description below. We'll be back next week for more Teach Me in 10, but if you can't wait until then, check out our Teach Me in 10 hub page where you can find a library of published videos. Bye for now.